So good afternoon. Thank you to the organizer for having me here. My talk will be from the theoretical side. I'm a theorist, so this sort of change of paradigm now. And I will tell you something about attempted solutions to the Hubble tension based on a varying equation of state for matter, and perhaps, if there's time, also something actually related to this afternoon session, which is CMB. So, what are the motivations? These are also questions that can be discussed later. Is the Hubble tension actually an indication for new physics? And from what I learned personally this morning, very interesting thoughts, how to explain the findings of this paper here, which I report here below. Was mentioned, of course, cited this morning. The first speaker, Abigail, is actually a co-author of this paper. And what intrigued me is this statement here: a result that's consistent with the current lambda CDM model, so no need to change. So I started wondering if there's actually a tension or not. So this is something which I think it has to be understood yet. Then can we solve the tension? I will mention various types of solutions. Mainly they are divided into early times solutions and late times solutions, all in the cosmological settings. And many of them introduce new degrees of freedom ad hoc. So this is somehow unsatisfactory to me, because they are introduced for the sole purpose. So I wonder if there is room in the lambda CDM in order to explain away the tension without these new fancy degrees of freedom, for example, early dark energy. And also many of the solutions, as I said, are ad hoc, so they solve or ease the Hubble tension, but many of them actually worsen the other tension, which is actually is an abuse. It's a slight discrepancy, maybe, is a better term, but I will abuse the term tension throughout the talk. And they worsen the S8 tension. So can we actually provide a solution which fits the cosmological pictures, not ad hoc, and solves also the other tensions that we know of? So I started to get interested after a paper that I will mention later about what happens if it's the equation of state of matter, of cold dark matter plus baryons, that changes. It is taken to be zero in the standard cosmological model, but actually what we call dust, so a pressureless perfect fluid, is quite different from early times, pre-recombination, and late times where structures form. So I'm referring to backreaction. Since general relativity is a very nonlinear theory of gravity, there might be an impact of small structure formations. From small scales to the larger ones, and so this sort of motivated to think, just starting to play around, what happens to the tension when we change a little W of matter. And further motivation was this paper by friends and colleagues of mine. Leonardo Gianni was a PhD student of mine in Brazil. They studied how, with a model based on spherical collapse, in order to model small-scale inhomogeneities. So that's why you see an R there, here. That's the radius of the initial inhomogeneity for actual overdensities and underdensities. And they show that taking this into account, you see in this plot you have on the y-axis the equation of state, W of matter, and versus the redshift. So it kind of fluctuates between positive and negative values. So I ask myself, what does it mean? What happens if W is positive or negative? in the perspective of the Hubble tension. With Hubble tension, with solution of the Hubble tension, I mean here to making the value derived from CMB larger in order to match the shoes determination using the distance ladder based on Cepheid variables. So we started from the qualitative analysis. So taking the first relation 2, which relates the sound horizon, R star, theta star, which is the acoustic angular scale, and this integral here, which takes into account, which is essentially the sound horizon, in fact, the comoving sound horizon. So it's the angular diameter distance to the last scattering surface. And these are the parameters determined by Planck. So theta is that number, and z star is that. The sound horizon is this value here. This has this formula here, where Cs is the speed of sound of the baryon photon fluid. As pre-recombination, baryon and photons were tightly coupled by Thomson scattering, essentially. And then you see the angular diameter distance to recombination. So the two classes of solutions that I mentioned earlier try to modify this relation, either acting on R star, so they are called early time solutions, so introducing maybe, for example, some degrees of freedom in pre-recombination physics, trying to lower R star, so increasing H naught, or late time solutions where they modify the left-hand side of that equation, number 5. So modifying the late time evolution of our universe, so introducing some different models, for example, of dark energy. When you determine H naught in the lambda CDM model, you essentially fit omega lambda in this formula here, and then compute H naught, and you find the well-known value. So what if we change a little bit the equation of state of matter? So we endow matter, so dark matter plus baryons, a non-zero W, a small w, I call it epsilon because I want it to be small. So we simply modify the left-hand side of the previous equation, equation 5, and in this way here, which we chose in order not to modify pre-recombination physics. So there is a sort of transition specified by a redshift, Zt, after which, this is just a toy model for the moment, after which the equation of state changes. And so the actual present time density parameter is the one at the bottom of the slide, number 9. And we started to do a qualitative analysis, okay, trying to fit in that relation between R star and the angular diameter distance to recombination. So if you choose Zt to be equal to the recombination redshift, about 1000, you find these values here. So with a small positive equation of state for matter, 0.003. So now this is a small value for the matter equation of state, but is it compatible with what we know about the properties of matter throughout the cosmic evolution? Well, there is this nice work here, according to which the correction has to be smaller than 0.01. So this finding here is perfectly safe. So this is the findings of that paper that I mentioned. So you see there are many models considered here in this paper. Varying W, also speed of sound is varying, and many constraints from many data sets. So you see there is no so zero is not really very well constrained, so you have some space for contemplating a different W, the W different from 0. And what we found, about 0.003, is well within these ranges here. And this is a plot that I made relating epsilon, so how much different from 0 is the equation of state, and small h on the horizontal. So you see, if you place the transition, the backwards you place the transition, the smaller the epsilon is needed in order to get a value, let's say, of h close to 0.7. And that's for the Hubble tension side. What about S8? So as I already mentioned, calling it a tension is maybe too harsh, but S8 is this combination here, given by the equation 13. And we have the determination conjoined by Kitz and Des in equation 14, and the extrapolation by Planck in equation 15. So there is a slight, it's not a tension, but there is a slight, very slight discrepancy. So thus, considering a different from 0 equation of state for matter, solve this discrepancy as well. So another qualitative analysis within this model in which the equation of state of matter is changed, there is one less complication with respect to models in which dark energy is evolving, because for us here dark energy is still lambda, which is if dark energy evolves with time, you have to carefully identify which part of dark energy the dark energy fluid is clustering and include it in the determination of S8. We have no this complication. So we simply have to substitute omega m with the omega m that I showed you earlier. And so you have this correction here in equation 16. But then we have somehow to also to calculate how sigma 8 is changed. Sigma 8 is related to the density contrast. Essentially, is proportion to the square root of the mean of delta squared. So it's related to the power spectrum, actually. So in order to estimate this, we started from perturbation theory. So this 17 is the equation, is the perturbed Einstein equation, the trace of the spatial trace of the perturbed Einstein equation. So it relates the evolution of the gravitational potential that we took to be just 1 instead of 2, assuming that there is no anisotropic stress. And for the sake of the example, we took delta p to 0. Then it's not difficult to solve that equation, just assuming the background that I gave you earlier. And we found this correction here, another factor here, 1 plus zt to this power, where epsilon, again, is the different from 0 equation of state. So if you put all these things together, so you get this alpha, this correction to the gravitational potential, about 0.96, with the same value of W that we used in order to solve the Hubble tension. And so the value of S8 is then lowered. So the same correction goes in the right direction for both the tensions, and that's nice. But as it was also discussed here quite extensively, it is quite possible that the tension on S8 requires a nonlinear solution. In fact, the scale is a scale 8 h minus 1 megaparsec, is a scale where the linear approximation is not yet, is no more good, in fact. But then this was a qualitative analysis, and I asked 2 collaborators of mine who are experts in a more thorough analysis to do this for this model. And unfortunately, what they found out is that it's the opposite. So data prefer the other direction, so a negative epsilon. So what we do with this model, we found a way to save him, by noticing that it is a competitive alternative to the CPL parameterization of dark energy. So instead of using CPL to explain those data and using extra parameter as W0 and WA, describing an evolving equation of state for dark energy, we use ZT and W for matter. And these are the corner plots that they produced. So if you choose, so the actual epsilon that was found by the analysis, it's quite negative, minus 0.5, which is also quite high, not necessarily in contrast with the previous work that I showed you, because they consider a different W for the whole cosmic history, so the effect of a different from zero equation of state for matter builds up until now. Whereas for us, since the nonlinear regime and non-viralized structures are important for the model that I proposed at the beginning, the paper that I showed at the beginning, we placed, so data prefer ZT placed at roughly 1. So you see some, so this is a nice alternative to the CPL parameterization, so thinking that W of matter can be different from 0 due to some backreaction. Just mentioning how can we mess around with CMB in order to solve the Hubble tension, so increasing the value of H0. There are some, not introducing new degrees of freedom, there are some proposals about changing the recombination process. So for example, modifying Z star, so at what time, what redshift it is the last scattering surface. So this is what people want to do with early times solutions. They want to move those contour plots of Planck in the concordance region with shoes and uncalibrated supernovae plus BAO. A nice proposal is, two nice proposals that I found in the literature are using primordial magnetic fields, for example, or this sort of obscure paper that I still have to understand more properly, increasing, so turning recombination more efficient by considering the excitation of kinetic degrees of freedom of hydrogen atoms. So modifying actually how the, so this is the moving towards the concordance region of the Planck results with respect to the tension S8. And this is the main idea of the first paper that I showed you about primordial magnetic field. The idea is to consider the Boltzmann equation for the capture process. Proton captures an electron, and considering an average. So since you have this relation in general, the recombination is enhanced. So it takes place slightly earlier. And this might solve the tension, the Hubble tension, because it decreases R star, decreases the sound horizon. But it has been pointed out that there is a problem with this approach, that is a conflict with the damping tail of the CMB spectrum, since the small scale physics is in fact modified. So what I think about this, what I thought about this, this enhancing recombination paradigm is perhaps we can consider a more complete hierarchy, the BBGKY hierarchy, so taking into account correlation between particle distribution. So you have here the standard approach for the collisional term on the right-hand side, where you see you can see Pauli blocking terms and Bose enhancement terms. Maybe if we, taking into account correlation, might produce extra terms, extra power of the electron fraction, free electron fraction in the collisional term. And if you take equation 30 as an example, you have this, you have that recombination takes place earlier. You have the free electron fraction, the function of the temperature, and the visibility function, so the probability that a photon, yes, is less scattered at some temperature. So if you use the equation that I showed you earlier, you find that the recombination redshift is slightly increased, and then the sound horizon is slightly decreased, leading again to a larger value of H naught, thereby solving the tension. So as conclusion, basically what I think it's important is that the possible solution has to fit the cosmological picture that we have. It should not be ad hoc, and possibly not introducing new degrees of freedom. So there is a sharp division between early times solutions and late times solutions, but perhaps as a final message, perhaps there is no the solution. Maybe the actual solution is a combination of small correction from both sides. So I leave you with this last slide. Thank you very much.
Hi, can you hear me?
Yes.
Thank you, very nice talk. And can you go back to slide 8? Here, the equation 12 is this the typical value to like you set omega lambda equal to this value, and you fix epsilon and z star, and you get this H naught? Is it just like a typical value test?
So, yes, you adjust omega lambda h squared as a single parameter in order to satisfy the constraint phi. Then once you have it, you sum all the physical parameters and you get H.
Okay. I see. Yeah. And can I ask why you choose like this for medicine, like equations of state is equal to 0 in parts, and it's jumped to a certain value at z star?
For simplicity.
Okay, I see.
Just to begin with, before going to more complicated models. Just see if there is potentiality to do something.
Yeah, yeah. Okay. Thank you. Yeah.
Thank you.
So I was wondering, if you prefer negative values of epsilon, will that not worsen the Hubble?
Yes. Yes, it does.
But you were inferring epsilon of minus 0.5?
Yes.
Okay.
Yes.
So,
but in a more complete analysis. So within this qualitative one,
so it
would
the
be a
behavior becomes
disaster.
non-linear further out, I'm guessing.
Yeah.
Okay. Thanks.
Thank you for the talk. This is the first time I've seen someone doing this with matter, and so I understand that it's important to look at the problem from this perspective as well. But I would imagine that it's also possible to argue that so one can say that matter is the part of the standard model of cosmology that we understand the best, and we understand how matter behaves. And so what would you say to such a critique who would say that, well, this is the one part that we know how to do, so they would, like, why tweak this part of the...
Well, do we understand really? I mean, we are... Yes. We model that matter as dust. It's a pressureless perfect fluid. That's it in cosmology. That's why also saying that lambda CDM is complete. I mean, we don't know what CDM is. So we are treating it, we have more theoretical grounds for lambda, but CDM is just treated phenomenologically in the cosmological picture.
Perhaps a follow-up question. You mentioned something about backreaction at the end.
Sorry?
You mentioned something about backreaction.
Yes, it was a broad...
That it could be a reason for why you get this. Can you explain that a bit more?
Yes, I mean, it's a finding of the paper that I cited here. Yes, here. So, due to nonlinearity in general relativity, small-scale clamping, as they treated them here, so as overdensities or voids, essentially, when they are not virialized, actually. So if they are virialized, the contribution to the equation of state, it has been shown also in the effective field theory paradigm, it's completely negligible. when they are non-viralized, yet they are viralizing, it has some impact on larger scales, on the cosmological ones.
Do you expect it to show up the way you saw it? Like with the parameterization you have for omega m? That's
Yes.
like
So I'm interpreting backreaction as a modification in W of matter.
I have a quick question. When you showed the 138 and 144 megaparsec at certain point, these can be interpreted also as the transition toward homogeneity and isotropy. These scales that alleviated the tension are could be comparable with the scale in which you have the transition with respect to the homogeneity and
Now,
it can be interpreted in this way or not?
no, these are sound horizons,
Yeah.
so computed just in the linear theory.
There is 120 megaparsec some years ago that was the scale at which people were searching for the transition to the homogeneity and the isotropy. So they are very nearby.
Similar, but I don't think they're related.
Okay, thank you.
So, strictly speaking, W is not zero, but proportional to the number density times the temperature, which is still much smaller than the energy density. But, so I was wondering whether can that be, can you estimate that, and how much is that compared to the deviation from zero that you had?
It's a nice point. I don't have an answer offhand, but since something, I think in that case, probably that applies to viralized structures. And in that case, actually, this whole picture doesn't work. It is strictly necessary that the nonlinear process is beginning. That's why we chose, it has been shown by the analysis that we have to start from actually a small redshift, transition redshift, which is 1. But that's, of course, your point is something worth of further consideration.
So I wanted to ask if you've thought about the impact on the KEQ scale, the turnover in the matter power spectrum. How does your model affect that?
The impact
On the
matter power spectrum?
yeah, and on the turnover scale, which is
No, there should be no impact on that, because it's still full in the linear part.
But because of differences in the omega m and omega lambda?
Maybe a slight shift, but not.
Because I thought you were fixing omega lambda h squared at like the standard value. Therefore, because h is different, omega lambda is...
But also what you call matter content is changed. It's not the omega m that we have for Planck.
No.
It's corrected by the 1 plus transition redshift to minus epsilon. So this interplay, I mean, the power spectrum should change on smaller scales. Should be a little bit damped. It should be
But around the peak, it won't really matter. Okay.
Not 100% sure, but I don't think so.
There's something to check. There's some reasonably accurate measurements of KEQ.
Yeah, no, you're right. In fact, it's follow-up investigation too.
Thanks.
Thank you. Oh yes. Oh, thank you.